Welcome to your Algebra 2 Lesson 4.5 and 4.6. For 4.5, we're going to solve quadratic equations by finding square roots. So that is your objective for today. And so we need to go over some properties of square roots. The first one is the product property, and these hold if you've got A being a positive number and B being a positive number. So the square root of A times B equals the square root of A times the square root of B. So if you've got the square root of 18, you can split it up as the square root of 9 times the square root of 2, since 9 times 2 equals 18. And this is nice because it lets us simplify, because the square root of 9 is 3. So you end up with 3 times the square root of 2. The quotient property has the same restriction. A has to be greater than 0, B has to be greater than 0. If that's true, then the square root of A divided by B is equal to the square root of A divided by the square root of B. So if we have square root of 2 over 25, we can split that up as square root of 2 over square root of 25, which is nice because square root of 25 is 5, and so we end up with square root of 2 over 5. Now, you need to know what it means to have a simplified square root. These properties are used to simplify expressions containing square roots. A square root expression is simplified if no radicand has a perfect square factor other than 1, and there is no radical in the denominator. You also can't have a fraction under a radical or in the radicand. Note that the symbol square root there means the positive square root. So the square root sign equals positive. So we want to simplify the expression square root of 80. We want to split it up. You want to think of a perfect square factor of 80. So 80 is equal to 16 times 5. 16 is a perfect square. It's equal to 4 squared. So you want to split 80 into 16 times 5. So we've got square root of 16 times square root of 5. Square root of 16 is 4. And so we can write it as 4 square root of 5. If you start off with something like square root of 6 times square root of 21, neither one of those can be simplified. So what you can do is multiply them together underneath one square root sign. The property lets us go in that direction too. And then you can start thinking of perfect square factors. So let's see, 126 equals 9 times 14. So we can think of the square root of 126 as square root of 9 times square root of 14. Square root of 9 is 3, and so we get 3 square root of 14. Square root of 4 over 81. Let's see, we can't reduce inside the fraction, so let's do square root of top over square root of bottom. Square root of 4 is 2, square root of 81 is 9, and so we end up with 2/9. And it's in simplest form because you do not have a radical in the denominator, no more square root in the denominator, and you don't have a fraction in the radicand. So over here we knew this wasn't in simplified form because we had a fraction in our radicand. Square root of 7 over 16 is square root of 7 over square root of 16. Nothing we can do about square root of 7. Square root of 16 is 4, but this is still good for us because you can have a square root on top, you just can't have one on bottom. Which brings us to rationalizing the denominator. Suppose the denominator has a simplified square root in the denominator. This is considered bad form. We must eliminate the radical from the denominator. This process is called rationalizing the denominator. And the reason we do that is because if we have to add fractions together, we want them to be in a simple form. We don't want to have to deal with square roots and that sort of thing when we're finding common denominators. So if you have just a number, square root of some number, then you're going to multiply the numerator and denominator by the square root of that same number. So if you've got square root of b in your denominator, you need to multiply the numerator and the denominator by square root of b. If you have a plus the square root of b, you have to multiply by what's called its conjugate, so a minus square root of b. Same thing as if you have a minus square root of b, you have to multiply by its conjugate, which is a plus square root of b. So conjugates have the same terms, but one of them has a plus and the other one has a minus. So again, they're called conjugates of each other, and their product is always a rational number. That's why we use them when we're rationalizing the denominator. Let's look at examples. Alright, I've got square root of 5/2. Well, that's a problem because I've got a fraction in my radicand. So I'm going to do square root of 5 over square root of 2. Neither one of those can be simplified. Not a big deal for the numerator. it is a big deal for the denominator. So we have to rationalize the denominator. This is that square root of b form. It's just the square root of a number. So whenever you have that, you just multiply on top and bottom by the same number. So I'm going to multiply on top and bottom by square root of 2. Okay, square root of 2 times square root of 2 is 2. Okay, because you would get square root of 2 times 2 is 4, square root of 4 is 2. On top, you just do square root of 5 times 2 is 10. And that's it. That's all you can do. Okay, so if I've got 3 over 7 plus square root of 2, I'm going to multiply on top and bottom by the conjugate of 7 plus square root of 2. So I'm going to multiply on top and bottom by 7 minus square root of 2. So on top, I'm just going to distribute that 3. 3 times 7 is 21. And then minus 3 times square root of 2 is 3 square root of 2. On the bottom, I'm going to FOIL out 7 plus square root of 2 times 7 minus square root of 2. 7 times 7 is 49. 7 times negative square root of 2 is negative 7 square root of 2. And then 7 times square root of 2 is going to be plus 7 times square root of 2. And again, square root of 2 times square root of 2 is square root of 4, which is 2. So we have a plus times a minus, so we have a minus. Square root of 2 times square root of 2 is 2. Notice that the middle terms here, the negative 7 square root of 2 plus 7 square root of 2, those zero out. That will always happen when you multiply by conjugates, and that's why we always get a rational number. So 49 minus 2 is 47, and so we have 21 minus 3 square roots of 2 over 47. Okay, so we want to be able to solve quadratic equations. And you can use square roots to solve quadratic equations without a linear x term. For example, if s is greater than 0, then the equation x squared equals s has two real number solutions. X equals square root of s and x equals negative square root of s. These solutions are often written as x equals plus or minus square root of s. So if I've got 3x squared plus 5 equals 41, what I can do after writing the original equation is just subtract the 5 over, and I get 3x squared equals 36, divide both sides by 3, and I get x squared equals 12, and then I take the square root of each side, remembering to put plus or minus on the side where the number is. So x equals plus or minus the square root of 12. Now I simplify square root of 12. I use the product property to write square root of 12 as square root of 4 times square root of 3. So I have x equals plus minus square root of 4 times square root of 3. Square root of 4 is 2. And so I get x equals positive or negative 2 square root of 3. So you have two solutions, 2 square root of 3 and negative 2 square root of 3. If you want to leave it written in the plus minus form, that's fine. Okay, let's move on to complex numbers. Lesson 4.6. So today you're going to perform operations with complex numbers. You're going to learn what they are. The first thing you need to learn is the imaginary unit. I equals the square root of negative 1. Up till now you've always been told, well, that's undefined. That's right. It's undefined in real numbers, but it's not undefined in complex or imaginary numbers. So let's talk about the square root of a negative number, because now we're going to broaden our definitions where we can actually simplify the square root of a negative number. If r is a positive real number, then the square root of negative r is equal to I times the square root of r. So the square root of negative 3 is equal to I times the square root of 3, because it's the same thing as having the square root of negative 1 times the square root of 3. Square root of negative 1 is I. By property 1, it follows that I times the square root of r squared is equal to negative r, because I squared equals negative 1. And square root of r times square root of r is equal to r. So if I have I square root of 3 squared, that's going to give me I squared times square root of 3 squared is 3. I squared is negative 1. Negative 1 times 3 is negative 3. All right, we're actually going to solve a quadratic equation where we use this. So this is very similar to the last example we saw in our last section. So we're going to subtract 11 from both sides, and we get 2x squared equals negative 48. We're going to divide both sides by 2, and we get x squared equals negative 24. Now we're going to take the square root of both sides, taking care to put plus or minus on the side that has just the numbers. Okay, so first thing we do is we put our I out, and so we have x equals plus or minus I square root of 24. Okay, once the I comes out, the negative's gone away, because what we've really done is factored out a square root of -1 and changed it to I. Now we simplify square root of 24 like we always have. We think of the largest perfect square factor. Let's see, 24 is equal to 4 times 6. So it would be plus or minus I, square root of 4 times square root of 6. Square root of 4 is 2, so we write it as plus or minus 2I square root of 6. So there's two solutions, 2I square root of 6 and negative 2I square root of 6. Okay, and again, you can write it just as plus minus 2I square root of 6. All right, so numbers with i's are imaginary numbers. Numbers with i's and a real component are called complex numbers. So complex numbers are a number a plus bi, where a and b are real numbers. The number a is the real part of the complex number, and the number bi is the imaginary part. An imaginary number is a complex number a plus bi where b is not equal to 0. A pure imaginary number is a complex number a plus bi where b does not equal 0 and a does equal 0. So a pure imaginary number is something like 3i. An imaginary number can be just a complex number like 2 plus 4i. A real number is a complex number a plus bi where b equals 0. And those are the numbers you've dealt with up until now. It can be 3, it can be square root of 7, it can be pi, it can be 2/5. That is a real number, but all of them are complex numbers. Complex numbers is your big umbrella. Okay, so here's our complex numbers. Okay, so you can see the exact relationship. So here are our real numbers, 3, -1, pi. Here are our imaginary numbers, 2 plus 3i, 5 minus 2i. And then within that imaginary numbers, there's a subset of pure imaginary numbers, things like 3i and -i. Two complex numbers, a plus bi and c plus di, are equal if and only if a equals c and b equals d. So if the real parts are equal and the imaginary parts are equal, then the whole complex numbers are equal. So 2 minus 3i equals 2 minus 3i because the real parts match up and the imaginary parts. Sums and differences of complex numbers. The book has you kind of go through some gymnastics here. Here's the deal. Just add the real parts together and the imaginary parts together. Kind of treat them like like terms. Okay, that's the easiest way to do it. So if I'm going to do 8 minus I plus 5 plus 4i, I'm going to do 8 plus 5. Let's get to that. I'm just going to do 8 plus 5 because those are the real components, plus -i plus 4i because those are the imaginary components. And then I'm going to write it in standard form. So 8 plus 5 is 13. -i plus 4i is 3i, so I have 13 plus 3i. So I almost treat I like a variable as long as you're adding or subtracting. There's going to be one case where we do something special. That's if you end up with an I squared, you have to replace the I squared with -1. Okay, I is equal to square root of -1. We prefer I to writing square root of -1. I squared, though, is equal to just -1, not negatives or square root of -1. It's just plain -1, and so we prefer that. But we won't worry about that right now, only when we get to multiply. All right, if I've got 7 minus 6i minus 3 minus 6i, I'm just going to treat it like it's a variable. So I'm going to have 7 minus 6i minus 3 plus 6i because we distribute the minus. So 7 minus 3 is going to give me 4. Negative 6i plus 6i gives me 0i. So it's just 4. That's it. Let's look at this one. We're going to distribute the negative sign there, or the minus sign. So we're going to have 10 minus 6 minus 7i plus 4i. So let's see, 10 minus 6 is 4. Negative 7i plus 4i is negative 3i. So 4 minus 3i is our answer. All right, multiplying complex numbers. Remember, you're probably going to have to distribute or FOIL, and always simplify I squared as -1 because I is the square root of -1, and once we square it, the square and square root cancel, you get -1. And just like hopefully you prefer the company of real friends to imaginary friends, we prefer a real number expression to an imaginary number expression. So I squared is always written as -1. All right, So let's look at A. We've got 4I times negative 6 plus I. So you want to apply the distributive property. So let's see, 4 times negative 6 is negative 24I. And then plus 4I times I is going to be 4I squared. All right, this is where we have to remember that I isn't really a variable. Okay, it really means something, and I squared equals negative 1. So we're going to substitute negative 1 for I squared, and so we have negative 24I plus negative 4 or negative 24I minus 4. So we like leaving i's in the answer. It looks nicer than square root of negative 1, and it reminds everybody, oh yeah, that's an imaginary component. But I squared is equal to negative 1, so we prefer the negative 1. So we always substitute negative 1 for I squared. All right, we want to write it in standard form, the A plus BI form, so negative 4 minus 24I. All right, so for this one, 9 minus 2I times negative 4 plus 7I, we're going to have to FOIL, okay? So we're going to multiply using FOIL, so 9 times negative 4 is negative 36. Let's see, negative 2I times negative 4 is 8I. 9 times 7I is 63I, and then negative 2I times 7I, let's see, 2 times 7 is 14. I times I is I squared. So we're going to simplify and use I squared equals negative 1. So we're going to substitute negative 1 in for I squared. 8 plus 63 is 71, so we've got 71 i's. So we've got negative 36 plus 71i minus 4 times negative 1. Not minus 4 times negative 1, minus 14 times negative 1. So negative 36 plus 71i plus 14 is going to give me negative 22 plus 71i. Okay, complex conjugates. The product of complex conjugates is always a real number. This fact will help you write the quotient of two complex numbers in standard form. So if I've got 7 plus 5i over 1 minus 4i, and I want to write it in standard form, A plus BI form, I'm going to multiply on top and bottom by 1 plus 4i. So on top, I'm going to have to use FOIL. So that'll give me 7 plus 28i plus 5i plus 20i squared. On the bottom, I'm going to have 1 plus 4i minus 16i squared. I'm going to substitute negative 1 for I squared. So I'm going to have 7 plus 33i, because 28i plus 5i is 33i, plus 20 times negative 1. On the bottom, I'm going to have 1 minus 16 times negative 1. So if I simplify, that gives me 7 minus 20, so negative 13, plus 33i. On the bottom, I have 1 minus negative 16, so 1 plus 16, which is 17. And then I just split it up. So I'm going to put I'm going to do the real component over my denominator plus my imaginary component over the denominator. So I'm going to have negative 13 seventeenths plus 33 seventeenths I. And that's it. Okay, guys, try the problems to try on your own. If you need to, rewatch some of the video. Come see me if you need my help. I will see you in class. I hope you have a great day.